Thank you. Good morning, everyone. I'm Aarohi Vijh from Alta Devices. And Alta is a company that makes a certain kind of solar cell, a very special kind that I want to tell you about today. This is actually our third time presenting at this wonderful event. We're very happy to return. And thank you to the organizers, particularly Dr. Brian Seeley, for having us again this year. So some of you have heard us speak here before. So we talked in the past years about some of the solar basics, some of the environment, the illumination conditions at high altitudes that pertain to aircraft and solar applied to aircraft. We also, last year, talked more about some of the semiconductor technology and so on that goes with the solar. This year, I do have an introduction, but I'd like to focus on a very important development that's happened at Alta Devices, and that's a further weight reduction that we've been able to achieve for our solar cells. So that's kind of the meat of my presentation, but I do have an introduction here. So just to place sort of the reason for existence of Alta Devices into concept, I'd like to just talk about all the disruption that we are seeing in other technological areas, not in solar or in energy, but in other areas over the last 15, 20 years. So here's an example from telecom. We're all very familiar with this, going from payphones to the early cell phones to now the Apple Watch. Just a huge amount of disruption that's happening in communication and signal processing. Same thing happening in sensors, right? So if you thought of a sensor on an automobile, chances are that you were thinking of a failed oxygen sensor or something like that. And now you have all these LiDAR, radar, ultrasonic sensors in vehicles providing all these functions. So it's just unlike anything 20 years ago. Electric vehicles, we know where that's gone, right? From golf carts to mainstream on-the-road vehicles. And of course, in the air, right? So here I've picked a photo of the Airbus eFan, but here at this forum, we're aware of all the work that's been done by so many groups in this area. A lot of excitement happening in electric propulsion. Same thing happening in data. So, in computing, we've gone from a single isolated computer to a network of computers to now what we call big data. So the curious thing about big data is that the people who are utilizing the data is quite different from the people who are generating it. And this is perhaps a first in the history of computing. So a lot of new applications are coming out of the existence and availability of this big data. Again, in the wearable space, wearable technology used to mean like a watch or maybe a better shoe or something like that. But now there's a lot of electronics and a lot of connectivity going into wearables, as we know, whether it's fitness trackers, whether it's more advanced watches. Smart textiles are coming. People are building a lot of smarts into athletic goods, but also into medical devices, wearable medical devices for nurses, for doctors, and for other industrial and commercial applications as well. So, you can imagine that if you want these applications to reach their full potential, right, you kind of want them to operate independently of the grid. And what does that mean? So in terms of connectivity, obviously, wireless is better than wired. So if you have an RF connection, then that kind of frees you to some extent. Then you have something called local or edge computing. It's called edge computing. And what that means is that you try to put a lot of the smarts on the local device itself. So whether it's an airplane or it's a phone or it's a car, a self-driving car, you're trying to do a lot of the computation on board the device. And a couple of reasons for that. First of all, you have response times and so on. And then you also avoid reliance on a supercomputer that might be on the cloud. So if that connectivity fails, your device still continues to work. So I think in the presentation from Faraday, we heard about this incident where a remote control aircraft flew through an ILS beam, and then that jammed the signal and caused it to crash. So that's a good reason for why you want to have this edge computing or this local computing. But the third piece of it really is what we call autonomous energy. So how do you have a source of energy that supports the autonomous mode of operation? And mostly, this has meant batteries, right? But battery technology has not really kept up with the speed of the advances that we are seeing in other technological areas. So batteries have become a bottleneck. And really here, what we are trying to say is that access to energy when and where it is needed is the challenge. So it's all about the time value and the location value of energy, right? So this is leading to people looking at harvesting energy from a number of different sources. So if you have access to flow of heat, you can try and use that. If you have mechanical energy, whether it's vibration or maybe it's regenerative braking, or last year I think we heard about windmilling propellers during the descent phase of flight. You can try and grab some of that energy. And of course, if you have sunshine available, then solar can be a good way to do it. So here, what I have here is a photo of from a current refugee crisis. So this is happening on the border of Myanmar and Bangladesh right now. So these folks are having to migrate from Myanmar to Bangladesh. And they all have, this is the 21st century, so they all have their electronic devices with them. You see that he's doing something on a cell phone over there. And they have solar panels with them to recharge these devices. So it works, but this type of solar panel does not really, it's not integrating into the product, and it's not integrating and it's not really addressing the challenges of their current lifestyle. So what do we want from the ideal source of autonomous energy, right? So the presentation from Dr. Tomasik this morning from Pipistrel, there was this reference to this mysterious black box, right? A power generation module, right? So what do you want from an ideal power generation module? You want lots of power. You don't want it to affect the form of the product, right? So you want it to blend in and to merge with the product and assume the form of the product. And you don't want it to compromise the product performance. So you don't want it to stick out. You don't want it to increase weight, increase drag, ideally increase the cost. So that's really what we are, that's the ideal that you are to have in mind. So how does that apply to solar cells? So most solar cells are made from a semiconductor material called silicon. And so if you have solar panels on the roof of your house or you see them along the side of the highway, chances are they're made from silicon. So silicon comes from sand. Sand is silicon oxide. You refine it, get the silicon out, melt it, cast it into these wafers, and make solar cells out of them. From the DLR presentation, you saw that the cost of this kind of solar has come down a lot, right? It's now competitive with many conventional forms of energy. However, silicon does have some limitations. It is what's known as an indirect bandgap semiconductor, and that has a couple of consequences. First of all, it means that you have to use a relatively thick layer of silicon to absorb light. And this means that you end up with a product that is heavier and it's not flexible, and it is also susceptible to cracking because it's brittle. The second consequence of the indirect bandgap is that it's not as efficient as some other kinds of semiconductors. So here we have this photo here is of a solar cell that's used in satellites for space applications. It's made from a family of semiconductors called gallium arsenide. And gallium arsenide is a direct bandgap semiconductor, and it's superior to silicon in a lot of ways. You get much higher conversion efficiencies, but also because it's a direct bandgap semiconductor, you actually need to use only a very thin layer of the actual material to get a very high efficiency. The disadvantage of gallium arsenide has been that as a material, as a raw material, it's somewhat more expensive than silicon. So this has kept the mainstream solar industry from adopting this material, even though it's much more superior in terms of performance. So what we are doing here in this concept is that we're exploiting the fact that you need a very thin layer of gallium arsenide only to make an efficient solar cell. So what we're doing is we are starting with a gallium arsenide wafer that doesn't look unlike this one. And you grow a solar layer on top of it, and then you peel it off, and you lift it off. So this has two consequences. One is that you can reuse this template many, many times over again. And that helps to reduce the cost. So essentially, you took what's a very material-intensive good, and you've made it into a manufacturing-intensive good that responds very well to scale up. So as you scale up, the costs come down for this. As you scale this up, the costs really do not come down much. And of course, the second side effect of this is that you end up with a solar cell that's extremely thin and lightweight. So it becomes very useful for certain kinds of applications. So yeah, this is the summary of the liftoff. You grow the solar layers in a wafer, you peel them off, process them into finished cells, and then you reuse the wafer. So this reduces the weight, the cost, and the environmental impact of the gallium arsenide solar cell manufacturing process. Some numbers in case you're curious. So gallium arsenide can produce it has a higher theoretical efficiency compared to silicon, a higher demonstrated record efficiency, which is held by Alta Devices. It also has a much higher efficiency in routine production. We're hitting about 26 to 27% in production. The actual semiconductor thickness needed is only about 2 microns as compared to 125 microns. So if you're not very familiar with this unit, human hair is about 50 microns thick. So if you look at just the weight of just the basic layer itself, and you look at how much power it's putting out, the power to weight limit, the theoretical limit for thin gallium arsenide solar cells is something like 31,000 watts per kilogram. So solar cells are a power generation device. They're rated in watts, and you can get 31,000 watts per kilogram in theory. With silicon, even if you didn't have anything other than the semiconductor itself, you're stuck at around 1,000. In terms of productized power to weight, so in a realistic form, right, with connections, with protections, and so on, with the thin gallium arsenide, you're still in excess of 1,000 watts per kilogram. Also, this stuff is, because it's so thin, and even though it's still a single crystal, by the way, very high quality, it's very low brittleness. It's pretty tough to mechanical vibration and impact. Also has a couple of other interesting properties like low light performance. It can operate pretty well, generate a good voltage even in very low illumination, like in this room even. And it also has an excellent thermal performance. So all solar cells, they actually, as they get hot, they tend to lose efficiency, they tend to lose output. But in the case of gallium arsenide, that happens to a very, very small degree. And so the thermal performance is excellent, which is important for some applications. We also have another technology that I'm not talking about too much today called the 2-junction thin gallium arsenide. We've set the world record for this twice. And the performance of that is about 15% higher relative to even this thin gallium arsenide. And then there's no weight penalty. So there's some headroom that we've got to improve that. So at Alta, we are working to bring this very high efficiency gallium arsenide solar technology to broad markets. So previously, like I said, this was restricted to satellites and other very, very expensive and exotic applications. But we're now trying to scale it up and bring it to a variety of markets. We're in automotive, in the wearables and Internet of Things devices, UAVs, and I'll be talking much more about that in a minute, other kinds of mobile devices. We've also had a couple of space flights, so the satellite industry is also getting interested in the low cost and high performance of these kinds of cells. Basically, anything that moves and has a battery and is exposed to sunlight potentially is a target application for these. So what does this look like? I've got a sample over here, and later on I'll put it next to that table, next to that UAV there, so you can see. So it's very, very flexible, very lightweight. And you'll see other kinds of solar cells out there that look like this, but this is 2 to 3 times more powerful than anything else that looks like it. In fact, it's more powerful than most other solar cells out there. So you're looking at a power output of 250 to 260 watts per square meter. So the sun puts out at the surface of the Earth about 1,000 watts for every square meter, okay, roughly 100 watts a square foot. And out of that, you get a power output from this of 250 to 260 watts per square meter, about 23 watts per square foot. It has a very high packing density. So if you've looked at some of the other solar panels, you'll see a lot of gaps between the cells, or you'll see the cells have rounded corners and so on, and that reduces the packing factor, right? How much effective solar area you've got in your rectangle there. But you can see over here, and also in the sample, that it's got a very good packing factor. The weight, including interconnects, so it's actually in a semi-realistic form, is only 170 grams per square meter, or about half an ounce per square foot. And in that form, it's about 1,500 watts per kilogram, 700 watts per pound. So this is our new thing for this year. We've transitioned this Gen4 technology into production. So all the solar cells we're making now in our factory, which is here in Sunnyvale, is this Gen4. And we've achieved this by thinning down a lot of the extraneous layers. We've got some support layers and plastics and so on in addition to the semiconductor. And we've thinned those down to achieve this increase in specific power. But another nice thing is, because we've thinned the cells down, we now have a very smooth surface. And obviously that's better for a lot of applications. I won't spend a whole lot of time on this. This is basically battery replacement, but again, this is, it's all around the form factor and the low light performance of these devices. This is probably of a little bit more interest to us over here today, automotive. So it turns out that if you can put about 1 kilowatt of solar cells on an electric car in a place like California, you can get about 25 miles of driving range per day. And that's quite significant. So 1 kilowatt with our kind of solar technology that we're talking about is about 4 square meters, or roughly 43 square feet. So this is we built a few demo cars, or our parent company has built a few demo cars. And we've also announced now a major long-term initiative with Audi to start putting these on their future electric vehicles. So this application calls for very high efficiency. It's a power-hungry application. You need high-quality, good aesthetics, integration into all kinds of shapes. Thermal performance is very important. As we know, cars can get very hot. So to maintain power output at elevated temperatures is very important. Also, I didn't mention earlier, these gallium arsenide solar cells we make, they actually have an infrared reflector in them. They don't really rely on infrared light for their efficiency, so we just bounce it back off. That means that the cells are also running cooler, which helps with air conditioning loads and so on. Small fixed-wing unmanned UAVs, so we're doing a number of these projects. So as the beyond visual line of sight regulations develop here and in various countries, there's a desire to extend flight times. So whether it's more miles that you want to cover for linear inspections of roads and pipelines and so on, or more acres of land for agriculture, or just more loiter time, right, if you're trying to monitor a certain area. So that photo which I just showed you is from a company called SAS. This is a company, they have a location here in the US as well as in Europe. And they had their basic platform, which had about a 3-hour endurance and batteries, and they've built a couple of solar versions with that can get 5 to 8 hours of endurance. These small flying platforms we've done a lot of. Here's another example from AeroVironment. That's a name that's very familiar to many of us in this audience. I see Tyler over here somewhere. And okay. So this particular platform, I think there's there's some thousands of these out there in the field of this Puma. This solar version went from about a 3-hour to about a 10-hour flight time. So how does this happen? Well, these platforms actually do not consume a whole lot of power in cruise flight. So here's a simulation of the battery state of charge. So here on the vertical axis, you've got the battery charge, here you've got the time of day. So like 4 is 4 a.m., 12 is noon. So it turns out that, say you launch it before dawn, you launch it at 3 a.m., you find out the battery is flat by 5 a.m. So it's got about a 2-hour endurance there. But if you launch it at a little later in the day, you start to see that as the sun comes up, the discharge curve of the battery starts to flatten out, and then towards the middle of the day, you're actually accumulating extra charge in the battery, right? Now, if you launch it later in the day, you find that you might actually be clipping. So the sun comes up too soon, and your battery really hasn't discharged a whole lot, and you've nowhere to put that excess energy. You can, of course, choose to climb or go faster if you want to use that. So how much energy do you get from solar typically? It's 1,000 watts per square meter. And it depends on climate and location. So say you're in Phoenix, you can get about 5.8 hours equivalent of the 1,000 watt hours per square meter input. San Francisco would be a little bit lower. So where we know about this, you want solar to be effective, you want to have very high efficiency designs, and you want to operate them in a mode that's low power or maybe a very low duty factor, right? So it's charging when it's parked and so on. High altitude long endurance airplanes, this is another platform from AeroVironment that holds the world record for altitude, I think 98,000 feet. Very impressive. A lot of commercial interest now in these. To use them as pseudo-satellites. So essentially, it's a platform in the sky, and you can put any kind of payload you want on it. The nice thing is that they're closer to the ground, so you have lower latency, round-trip delays for communication. They're upgradable. You can retask them very easily, which you can't do with satellites. The thing is that they need constant propulsion, and they're extremely weight-sensitive, right? So if you want to put solar on this, you need low weight, high efficiency, environmental stability to deal with all the stuff up there, mechanical stability for the flexing. You need to support the aerodynamics of the airplane, right? And here, so this is actually from the Facebook Aquila info sheet. It says about half of the mass of the airplane is devoted to batteries. So I'll talk about this in a minute. That's kind of a limiting factor right now. This is basically saying that Alta's product that I just showed you is kind of in its own class in terms of watts per kilogram and watts per square meter. So very high efficiency combined with very, very low weight there. And because this is not very sensitive to UV and moisture and so on as compared to a lot of other solar technologies, you can get away with using a very basic, very lightweight encapsulation or lamination, which translates into a very, very good power to weight ratio at the finished product level. So what can you do with the weight saving with the lighter solar? Well, right now, most likely people in the high altitude market would probably use it for the battery because they're looking for a way to store all that energy to fly through the night, especially at high latitudes where the nights can be very long in winter. Take a quick look at this platform. So this is very, very familiar to all of us. Amazing achievement, right? A couple of years ago, this flew around the world completely on solar power. And I chose this because it has some public info out there. So it has a 270 square meter array with crystalline silicon cells, total rated power output of 66 kilowatts, weight of 2,300 kilograms, 5,100 pounds roughly. So that's using this silicon technology that they have. So this chart over here, we're going to make this presentation available later if you want to go through it, but the bottom line is with our Gen4 technology, you can get about 18% increase in power over the technology that was used by Solar Impulse 2. And you can have a 3.7%, almost 4% weight reduction. This weight reduction, by the way, is not just the reduction of the solar cells of the array. This is a weight reduction of the entire aircraft. So that's quite significant. With our Gen4 2 junction, you can get even more power, almost 30% more power. So you can fly faster, carry more, fly higher. You can carry a larger battery and have lower depth of discharge. You can make the airplane smaller, which can have a lot of benefits, as we all know. Electrically, these are very simple, about 1 volt per cell, and we work with customers to make these series parallel arrays for them. Structural integration, you can build them into carbon fiber, fiberglass foam. For quick tests, people even tape them onto the wing. We have a UAV demo on display over there on that table. So if you want to take a closer look at what it looks and feels like, feel free to walk up there and touch it and look at it. And we're doing a lot of testing, a lot of environmental testing and qualification in support of our customers right now. So we are here in Sunnyvale, California. We make everything in our factory here, about 250 employees, and we are slowly ramping our capacity to about 3 megawatts per year, which, to place it into context, is enough for about 50 solar impulse 2 size platforms annually. So I'll leave that summary up there and be happy to answer questions if we have time. And I want to say that, again, thank you for inviting us, and the purpose really for us to come here is to invite collaboration.
Thank you for that exciting new breakthrough. And of course, it makes us think about Eric Raymond and the Sunseeker duo, coated with solar cells and maintaining level flight just with the solar panels. Two quick questions, and I think to have our next lecture, we won't be able to extend questions, but I know many people will want to talk to you about this technology. When you glue these panels onto the surface of a wing, is there a particular specified adhesive? Can you use any spray-on glue? Is there a way that is compatible with the product? And secondly, as an interesting comment, the midday enhancement of solar power suggests that if we have urban air mobility where all the commuters move early in the morning and late in the day, the middle of the day can be an almost free deadhead flight to reposition the sky taxis at low power, low cruise, getting them back to where they're most necessary. So there may be an ideal mix here between daylight energy and the operation of a transit system. But about the glue.
Yeah, thank you, Dr. Seeley, for that comment. Yeah, I think that for high energy density platforms like VTOLs, I think, like you said, in the middle of the day, that's an attractive thing. And then also, yeah, anytime really when you have a low duty factor, right? So if it happens to be sitting out in the sun, why not pick up some charge? And if there's no cost to doing it in terms of weight and aerodynamics, then why not get some extra power? I agree. In terms of adhesive, the back on these is a type of polyester, and so that should give you some idea as to the types of adhesives you can use. But typically in aerospace, we want very, very high reliability, and so we end up working with specific materials and with customers to qualify their processes. And we're actually learning a lot from our space effort as well, because that's a high vacuum, very harsh environment with a lot of thermal cycles. So we're learning a lot about that, and we'd be happy to work with you to apply that to your benefit.